Thank you very much, Kai-Uwe, for this kind introduction. Thank you to IASS for conferring me with this great honor, with this medal. Unbelievable. I really say I've been completely surprised. I didn't expect it, and so it's, well. And another thank you for Carlos and the team for organizing this conference. So many attendees. I'm really, really happy, and I think you did a great job. And as far, I think you also can get an applause for what you did. Preparing this speech, I've been questioning myself: why am I standing here? I'm standing here since I'm working together with this wonderful, wonderful bunch of people. Almost 250 of them spread almost all over the world. We are in Europe and also in Shanghai and Melbourne. And without these people, none of these projects would have happened that I want to show you now. So I want to talk about the past, the future, and the present, so about everything. And I start the first project is pretty much connected with music, with jazz music, which I'm a very fan of. And this is Joe Zawinul. He was an Austrian jazz musician, and he was the man behind Miles Davis moving into electronic jazz. He was a keyboarder for things like Bitches Brew. And later he joined with Wayne Shorter for the group Weather Report. And in 98, Joe Zawinul, since he came from Vienna, Austria, was invited for a memorial concert at the site of the former Nazi concentration camp in Mauthausen. And the site is quite an impressive stone quarry. So to have a concert there, it came up the idea of having a cable net spanning over this quarry for two purposes. One is for acoustic sail above the stage to improve the acoustic, and to find a place to hang the loudspeakers and all the spotlights necessary. Well, 98 digital tools have been not so available. I will come back to this issue also for the other projects we did in the 90s. So we've tried to set up you can see a very rough model, try to identify the points where the cable net could be placed, and then of course you have to define the length of the cables, and here we could cooperate with a very, very competent contractor from Austria. And this is then the acoustic sails above the stage, and this was the event, though it was just a temporary structure, just for one night, for one concert. The next project is also connected with art. This is about Thomas Saraceno. For those of you who have attended the Hamburg Symposium 2 years ago, we had Thomas Saraceno as a keynote speaker. Thomas he studied in Argentina, in Buenos Aires, and then he came to Frankfurt to do a postgraduate architectural study at the Städelschule. That's where we met Thomas, and since more than 20 years we are cooperating with him. And he had come back to explain what you see. He's pretty much involved in the research for spiders, how spiders build their net, what type of nets they are building. Then his issue is to build accessible, one of his issues is to build accessible nets. where people can walk on. And so he developed the idea which is in Düsseldorf for the Kunsthaus K21. They have an inner court, and on top of this inner court there should be an accessible roof, and to have the necessary curvature for the cable net. Some high points had to be developed. We used the existing structures and add additional spheres where we could put the cable net on. And at the end of the day, it looked like this, and it was really a very big attraction, staying there for almost 1 year. People could go on the net, of course, with only a reduced number of people at the same time, but it was very prominent, and it was really an exciting event. A similar installation we did at a university, form finding for almost bending free hanging structure, interior structure, then a Voronoi structure. All these nodes are similar, each of them is different, so these nodes had to be, the geometry of this node had to be developed geometrically and then milled down. I'm sure most of you know this technology, but this has been 15 years ago, so at this time there was no Karamba or no tools available. We had to script it with Visual Basic and C++, and to find the nodes between the interfaces between the different programs. A similar project in a different scale, the self-supporting framework. This project, university project, together with Schneider Schumacher, Frankfurt-based architects, to explain more in detail. You see a sheet of paper, a folded sheet of paper, and due to the curvature, we have a structural stability. We have tension at the top edge and compression at the bottom and the center. So the compression is stabilized due to the curvature. If we get rid of the curvature, it's just a sheet of paper that hangs down. We have buckling of the edge. With this principle, of course, again, a structural optimization. We used ultra-high performance concrete with a micro mesh reinforcement. So the edge thickness has been only 25 millimeters. And for this project, we received in 6 years ago the Suboy Award for the best paper. We had a lot of fun developing this project. A similar thing we also did at university here. Our students did everything from the form optimization, form finding, form developing, form optimization, building the formwork, putting in the reinforcement, and mixing the concrete and pouring the concrete. For those of you who have worked with this ultra-high performance concrete, they know how sensitive this material is. So it's still existing. It's used as a kind of bench, Möbius bench. When I look back, this project we did for BMW in 1999, 20 years ago, for the International Automobile Exhibition in Frankfurt. At this time, BMW wanted to promote the hydrogen technology. 20 years ago, where are we now? I don't know what happened to the German car manufacturer, but this is another issue. So how do you build such a thing? We rationalized the structure in sections. Each of these sections then was set up with aluminum flats, and for the cladding we used acrylic glass, which you only have to heat up to 170 degrees, then you easily can bend it. So we had about 300 different sized, different shaped elements of acrylic glass, and a nice thing has been the door. How do you walk inside such a building? I said 20 years ago. For this project, I think we've been one of the first using Rhino, which at this time was still a beta version, which you could download using this Rhino for a professional project. But we had at this time we had no other chance, and it turned out to work quite well 20 years ago. A few years later, in 2003, Graz, which is in Austria, was elected as the cultural capital of Europe, and for this they launched a competition for a Kunsthaus, which should be erected not inside the old listed city, but outside as a kind of urban refurbishment of this area. It looks like a strange potato, but inside it's a real building with 2 floors. We optimized the form a bit, find this triangular shape. You see the hexagons for the skylight, which then should be prefabricated. You have to develop a scheme, and then you have to test it. You have to do a one-to-one mock-up, and this is the structure with these triangulated elements in between. The cladding was another question using acrylic glass, but acrylic glass is inflammable, so we had, together with the authorities, we had to find out the proper mixture. I think Harald Kloft is here. At those time we've been working together with him, and he was pretty much involved in all these details. Again, acrylic glass. You have to develop the geometry for each of these elements. You have to cut them. You have to bend it, and then they are shipped on site in this way. There have been no fixation. We had to develop all this fixing elements, how to fix it to the facade. You see. These things, this facade, or the roof, is it the roof or a facade, is sprinkled from above and from underneath, just to make sure that it is not inflammable. And this is the building, nice shape. And underneath this acrylic glass, there are some lights which are able to project moving pictures onto the thing, and this is the urban setting. And when you now go there, the urban idea worked. So people are crossing the River Mur. They are going on the other side, and this whole area, which is goes towards the main station of Graz, now has gone a real urban retrofitting. A jump in material. There was a competition for the Rolex Learning Center launched in 2005. We've been into this competition. We're already in the competition with Sanaa, Tokyo-based architects, and they developed just a one-story building sitting on a kind of landscape. And this was the challenge, having a shell. I really would not call it a shell. It's more a bended plate, which due to the bending induces a lot of normal forces. So we have a slenderness of 1/18, and it was really a challenge to do it. And we had two challenges. One is to find a system that could work, and the other then was how do we bring this information on site? How can we develop a formwork that has the necessary accuracy? So this was the idea of the restaurant of EPFL for the groundbreaking ceremony. Of course, course, we after having done our form optimization, minimizing the bending moments, we of course could then tell the site the XYZ coordinates of each point, and here they wanted to have it in a 50 centimeter grid, but which is, with this information you can build nothing. You can control what you have built later on. We had some experience of building double curved concrete walls from a project with Frank O'Geary, and so we transformed this experience into a horizontal. So we developed boxes 2.5 by 2.5 meters, each of them individually curved, individually shaped, and these boxes could easily be nailed together, then shipped on site, erected on a scaffolding with a certain height. At the end, we had this almost perfect surface that could give us the necessary accuracy. For the main reinforcement, rods with a diameter of 50 millimeter, 50, which had to be welded together, since an overlapping joint for such an element close to the surface is simply not possible. And this was the outcome. Being a structural engineer, I was satisfied. This could have stayed this way, just this flowing concrete surface. But this is the built thing. My next project, a few years later, again a concrete structure. What for? For the extension of the Städel Museum in Frankfurt, again with Schneider Schumacher architects. It's Frankfurt's most prominent fine art museum, and in the competition we developed a place for the extension, which was the garden. So underneath the garden we could have this thing, and having a concrete shell on top of it, curvature optimizing to minimize the bending forces. This is the surface. Then we have the skylights. We had to develop the exact geometry of the skylight, again mapping this skylights onto this rhino surface, and then a similar system like in Lausanne, but here we have an interior surface for a museum. So these are blocks of foam fiber covered with a fiber reinforced composite. These is just 1/4, though these elements could be used 4 times. And then when you look at the concrete, you see the reinforcement, you see the ductwork for the electrical cables, you see the tubes for the thermal activation. The rooms is heated and cooled with this slab. And last but not least, you see the post-tensioning cables for the area which is flat, which has no curvature. We all have been surprised by this surface. No one has seen such a thing before, and that's how it looks like today. This is the museum room, and the whole thing is open to the public. In summer, as you can see, it's used. People use it to walk on and to sit on this thing. The next project is again a concrete project, but here no curvature, but a folded concrete plate for the Dijkman Library in Oslo, which is still under construction. Why this cantilever of the uppermost floor? This cantilever was the idea of the architect, and already in the competition, to allow the visual contact, to allow the sight line to the opera house when you leave the main station. You should be able to see the opera, and so the space we took away for this sight line was then put into this cantilever on 2 sides. After discussing several alternatives, we ended up with having the roof as a folded plate which is cantilevering above this green line. So we have tension in the ridge and compression in the Aris line, where the compression goes onto these concrete columns. And then the floor underneath is suspended with this thin steel bars from the roof. And this is the construction site without the facade, the view to the opera house, the view from underneath. And this picture I took just 3 weeks ago. The opening will be in spring next year. In the last almost 25 years, we had quite a close cooperation with Coop Himmelblau, Vienna-based architects, and this project, for the UFA cinema in Dresden, was our first project. We did together with Coop Himmelblau, completed in '96. We started in '94. In '94, just AutoCAD 3D was available. Erststab moved into 3D structures. It was really a challenging thing in those days for us at least to do such a thing. We had a physical model, and we were on this physical model. Just by pressing on it, we could define where we need some extra diagonals, some extra struts to make this foyer happen and make it look like it looks now. Another thing with Coop Himmelblau is not the Olympic Stadium, but this building just on the side of the Olympic Stadium, the BMW Welt. The idea of the architect was a cloud, and underneath this cloud, the whole kind of marketplace where all the activities BMW wanted to concentrate in this building could happen. And the challenge was here on one side the structural system, and the other thing the system for the cladding to allow this open space to happen. And now BMW is telling that they have more visitors than Schloss Neuschwanstein, though it's the most attractive museum we have in Bavaria. The last project with Coop Himmelblau I want to show is the headquarters for the European Central Bank. Again, a competition. We started to talk about this competition in 2002. The completion was 2014, so 12 years of my life. 12 years of my life in this building. The project, the premises include the refurbishment of this existing market hall, a very interesting concrete shell structure built from the same team who built the planetarium for Carl Zeiss in Jena. They then moved over building this cylindrical shell roofs. So we did all the refurbishment in close connection with the authorities. The high-rise itself, just 2 towers connected via an atrium, and to make this structurally stable, we had to connect the 2 towers within the atrium. That means we had to develop a lattice system. The architect didn't want to have a regular system, so this was one of our first approaches to generic algorithms. We defined some rules and then let the computer set up this generic process. I think most of you are familiar with this, that you have to generate, evaluate, cross, and mutate from one generation to the next generation. And then the outcome in the beginning was we had a horizontal deflection of 400 millimeters, and we ended up of 235. Well, you must not look at the real number. It's just in this optimization process, so we could achieve quite a thing that is okay. Of course, then we had to do a real real second-order calculation, taking into account everything and taking into account also the twist of the whole building. It was quite a complex process, but for the first approach to position these diagonals, this was really interesting. The diagonals itself, up to a length of 60 meters, steel tube, 1 meter by 1 meter with 100 millimeter thick steel plates. These are the connectors that we had to put into the cores. These diagonals, being too heavy to be lifted in one part, had to be lifted in two parts and then welded together in situ. But at the end of the day, the proportions look okay. It looks looks good. And also from outside this building, due to this curvature of the surface, from every side you approach to the building, you find a different view. Just some more high rises we have been doing in Frankfurt. This is someone called it Europe's highest residential tower, 200 meters in the city of Frankfurt. And another thing just being completed right now with BIC, this tower with a hip shake. It's a mixed-use tower. You have offices in the lower part and offices in the higher part. And where we have this hip shake, there is a residential. What was here, one challenge was to do the construction pit, to do a 16-meter deep hole. So we had to do it in a top-down building, since the horizontal forces on the perimeter wall are too high. So we had to. The first thing we had to build is this -1 slab. Then we had to dig out, build this -3 slab, and then another digging process to find the level for the foundation slab. As I said, almost completed, but right now we are working on this 4 towers project called 4. Architect is Ben van Berkel, UN Studio in Amsterdam. Again, a mixture of residential hotel and also office building. Completion will be in 3 years. Canaletto in England. To be honest, we found this picture later when we have had completed the project. The project is on Frankfurt Air Base, not Air Base, sorry. The former air base was on the southern part, but Frankfurt Airport. This is the building you see here is a building sitting on the high-speed train station. And it was lacking a parking garage, so the idea was to have a parking garage just in the line of the building. And then you need a connection from the parking garage to the building, and this was a bit too boring, this type of bridge. So together with Lenkfeld and Wielich architects, we could bring in the idea of an irregular lattice girder. So again, using a generic algorithm, we had to define the maximum angle for the diagonals. We wanted to have only 2 layers of diagonals, and then set up an optimization process, and having the computer define the final position of the diagonals. This all has been done with Visual Basic, finding an interface between the geometry and the structure in 2 directions. And at this time, the colleagues in Vienna, together with the University für angewandte Kunst, got a research grant to develop Caramba, to bring this finite element directly into the rhino grasshopper family. And with this thing, you just can define any structure with grasshopper. You have to associate loads, you have to associate material properties, and then just by sitting on the screen, clicking, you can add struts, you can change the port conditions, and the program gives you a real-time answer in deflection or normal forces or bending moments, whatever you want. And I think quite a few of you are familiar with this thing, and we still use it for research. We still have this connection with the university and use it for real projects also. So this is the background, and then all of a sudden, to be honest, I have not been really aware of this, but in the last 4 years, this has become a main driver for us. What is the Paris Climate Agreement 2015? The nations signing this contract agreed on to minimize greenhouse gas emissions half by 2030, and then again half by 2040, and another half by 2050. This should happen in all these parts, the food production, for all this part, for transport, and also for buildings, which are we. All of you are here. We are the engineers, we are the architects, and this is our task, to minimize the CO2 production within the next 10 years for 50%. I have no idea how we can achieve this, and I would be happy if someone has some ideas. It's really an unbelievable task that we are confronted with, but we have to face it, since building and construction account for more than 35% of global final energy and use nearly 40% of energy-related CO2 emissions. So this is our thing. This should be our thing for the next decades. Another thing, worldwide cement production generates more CO2 than global air traffic. Then The Guardian, February this year, concrete, the most destructive material on Earth. The world is running out of sand. To be honest, 4 years ago, I thought we had sand like sand on the sea, but sand has really become a problem, especially in Southeast Asia and in the Middle East. And also here in Europe, in Germany, we have a problem. We are sitting on tons, on millions of cubic meters on sand. But if you want to open a sand quarry, you really run into severe problem. But on the global scope, the sand is really become a problem. So globally, we must phase out CO2 emissions to reach this 2-degree goal, and the critical importance will be this 2030 milestone. We have to try to minimize this CO2 reduction. If we cannot make this goal, then I think we will really have problems, and the researchers are telling us that climate change then will become irreversible. So again, this is the task for the next decade. So one step in this direction is reduce, reuse. That means reduce the material whenever possible. Forget the flat slab, go back to a beam and slab system. Reuse, we do not have to tear down everything, try to reuse existing structures, and if not possible, then we have to recycle. In Switzerland, they use the word urban mining. In Zurich, you have to reuse 50% of the material you have on site. Otherwise, you get no building permission. These are things we have to take care, and the other thing is that we have this wonderful material, wood, outside. The more timber you use, you take out CO2 and store it in your building. Well, it's not my word. It's Timber.com. They are selling timber, but anyway, we have to get it from somewhere. And there are so smart materials now on stage, like this cross-laminated timber. You can do wonderful things you normally would need concrete for, and even the load-bearing capacity of timber is similar to concrete. With the CLT, you can achieve thicknesses that are even smaller than a concrete slab. Just one project we finished in 2017 already. Modular system for extension of a school. When you look from outside, you attach a facade to it, neither from outside nor from inside. Here you see the timber, of course, but what you do not see, that is a modular structure. And beginning of this year, we've been working for Siemens campus in Erlangen, Siemens headquarters, so to say. We've been together with KSP, Jürgen Engel Architects. We designed a completely concrete building with a concrete flat slab, a span of 8.1 meter, which is normal, 30 centimeter thickness. And then they went onto the market, and then one company came using a system CRE that was developed by Romberg, an Austrian-based system. And what do? They have timber and concrete composite panels. They have Klulam columns for the facade, and in the steel they have a middle girder to collect the load, and then steel and concrete columns. And this is the way how the system looks like. These are the prefabricated elements. So also on site, we do not have to use so much concrete poured on place, which produces a lot of noise and garbage. That's how the system can look like. And then when you look around, in Norway, they have been building the world's tallest wooden building, Carbon 12 in Portland, Oregon. I personally, I'm not quite sure whether you should prove the capability of timber building high rises. Another discussion about safety, especially fire safety, but this is another discussion. I would prefer to use it for low-rise buildings. And this is the last project. It was a competition in Taijuan Botanical Garden. We've been in together with Delugan Meisel, Vienna-based architect, and we had the inspiration from this Chinese building technology with this cantilevers building, laying one beam onto the other. Of course, being a structural engineer, if you have beams laying one on top of each other, you want to connect them, you want to get the necessary shear stiffness to activate the structural height. There where we have this support, we have a bigger structural height, so the structure is more dense, and from underneath it looks like this. And then this is a rendering, and this is the real thing, how the things are built on site. And here you see the scale of the whole building. Still under construction, and the project contains three domes. Each of these domes will have a different climatic zone inside, and no regular symmetrical structure. But we wanted to open the building to the sun, to get as much sun into the building as possible. So we developed this structure with the two-layer beams in the primary load-bearing direction, and the other just for stabilization, just one layer. What you see blue is the roof structure itself, the tiling. For the blue part, we can use flat elements, and only where the curvature is getting yellow and red, we have to curve the glass elements. And this is a rendering. Another thing is when you attach a beam in such a direction on a sphere, you get some torsion to have the surface of the beam perpendicular to the surface of the structure. So each of these beams are then milled down in a way that the surface is parallel. So these beams are again individual beams that just sit on that place. And the last thing I wanted to state here is we have no experience with rammed earth with this material, but this material is around, and I think this is a good time to talk about, at least to give you the idea that there is something new. And in Austria we have Martin Rauch from Lehmton Erde, who's been building this Ricola, the facade, the exterior wall for this Ricola Kräuterzentrum, together with Herzog Demeron. Here you see the happy architect Pierre Demeron with the building. And in Darmstadt, close to Frankfurt, just this year been completed the Alnatura campus. Again, we have rammed earth elements. And the last picture I want to show is a house in Weilburg, which is about 100 kilometers north of Frankfurt on the River Lahn. It has been completed in 1828, 190 years old, and it's a rammed earth building and still occupied. So this could be the challenge. Thank you very much for your attention.